So I've just started grading the midterm, and things are looking okay. A few questions, there were some confusions, but a few questions. I was very impressed by all of your work. So yeah, I wanted to quickly walk through a couple of the questions because I thought that would probably be beneficial. Yeah, overall, quite solid. I'm hoping that your grades will be published in at least a week from today. It's just me grading them. I just want to make sure that everything is graded fairly, so I'm not letting TAs or anyone grade it. So I'm going through it, so that's why it's taking a little long. As far as all of your lab assignments and homework assignments, they are being aggressively graded right now. You should have a lot of your grades released this week, and then you will have the rest of them within the next couple weeks. And yeah, so you should have all of your grades in very soon. Okay, so the first question that I want to just briefly mention. Okay, so I'll read it really quick. So here is a CMOS circuit. So we can see we have a bunch of muxes, or sorry, we have a bunch of MOSFETs connected in this way, and then we were asked to fill out this waveform depending on these inputs right here. Okay, so can anyone tell me the first thing that you noticed on this and that led you to your first thing that you filled in here? What's the first thing that we noticed with this? Yeah. Yeah, right. So this structure right here is an inverter. Whenever you have a PMOS on top and MOS on the bottom, and they're both connected, the gates are connected together, this is the exact same thing as an inverter. Okay, how many of you saw this? And you were like, oh, yes, that's an inverter. Okay, great, perfect. Yeah, so what we can do is we can basically just like ignore this whole thing right here. So ignore all this, and this is just an inverter. Okay, and then same over here. We can just ignore this whole thing right here, and this is also an inverter. Okay, so that helps. So what is the first wave that we could probably fill in? Shout it out. Y0, yeah. Y0 is going to be what? The opposite of A, exactly, yeah, thank you. So, yeah, so Y0, so it starts out at 0, goes up to 1, down to 0, up to 1. All right, so this is Y0. It is just exactly opposite of A. Okay, but now we passed into this thing. All right, okay. So, well, when A is 0, then what will the output of this be? Do we remember? So if A is 0, so there would be a 0 here, and there would be a 1 right here, and a 0 right here. So which would the top or the bottom transmission gate be on? Top or the bottom? The top one, yeah, right? Because just in general, whenever you have a PMOS that's connected to 0 and you have an NMOS that's connected to 1, that means that there is a short circuit. And so therefore, whenever you have this 0 case right here, then these are connected. However, now if you were to have it be, whatever, now A is equal to 1, so not A is 0, A is 1, then in that case, will the top or the bottom transmission gate be activated? Bottom, okay. So therefore, we can look at Y1, and we can see, I'm gonna change the color of this. So, red, okay. So if Y0 is 0, yeah, sorry. Okay, so if A is 1, right, then what will the value of Y1 be? Like, will it be B or C if it's 1? Let me rephrase it. So what will the value of Y1 be? So what will the output right here be? And your two options are either B or C. What will the output be if A is 1? Yeah, it'll be C. So I'm going to write that in. So I'm going to say, just at first, I'm just going to write that in. So okay, so for every time that we have A is equal to 1, then we're going to have C. Otherwise, we are going to have what value? What is it? B, yeah, okay. Yeah, there we go. So this is how I thought about it. And then now we can just look at whatever the value of C and B and C and B are at each one of these steps. So then we can just draw that out. So we say that C, so what is the current value of C? 0, okay. What is the current value of B now? 1, okay. What is the new value of C? 0. What is the new value of B? 0. Okay, good. Right? So passes through only the one that we are turning on, and it looks like B is the only time that we have a 1 in the sequence. Okay? And then finally, Y2 is just an inverter, so therefore it will just be exactly opposite of Y1. So now it will be this. Sorry, not quite. Yes. There we go. Okay. Does this make sense? Yeah. Is this what everyone got? Yeah. Okay. Any questions on this? Does it kind of make sense now if maybe we missed it? Any questions? Yeah. Okay. Cool. So yeah, kind of a tricky question. Deals with, yeah, we have a CMOS inverter, and then we have 2 transmission gates. Also, what circuit is this right here? Anyone know? What is it? Transmission gate. Sure. So there's 2 transmission gates here, but what does this kind of look like? Like if we were to draw this as a higher level circuit that we have been using, just this specific part right here with 2 transmission gates in parallel. What is it? Not quite XOR. Close. What is it? Yeah, MUX2. So notice that our select is basically just A, and then B and C are just our like 0 and 1 inputs. So this is actually how you can create a MUX. And I guess, yeah, technically that would also include this inverter right here. So yeah, so this whole circuit right there is a MUX. And so by just putting an inverter at the end right there, we actually call this an inverted MUX. Yeah, or MUX I2. So if you go into the Skywin 30 PDK and pull up the MUX I2 cell, this is actually what it looks like. Yeah. Okay, cool, great. Okay. And a reason that this is useful is because if just transmission gates can actually take quite a bit of current to drive them. They are yeah, whatever. They just take a lot of power. And so because of that, oftentimes you will see another set of inverters on the B input and the C input, just to have like enough, like a really good, strong like driver into these transmission gates. So what you'll most likely see in like a real MUX cell is you'll see like an inverter here, but then you'll also see an inverter here, an inverter here, and then it will cancel out with a second inverter at the very end. So then it will just be a regular MUX cell. So yeah, a regular MUX actually ends up usually having 4 inverters and 2 transmission gates. That is generally how you implement a MUX. All right. Cool. So then I wanted to briefly talk about, I wanted to talk about now the counter question. This was also a question that I saw not everyone fully understand. So for the equals to 5 unit, most people were able to get this question, but okay, so what is the sum of products expression given the input A2, A1, A0, where in terms of A2, A1, A0, we will have a 1 only if this input equals 5. So what is this expression? Any volunteers? Yeah.
Is it A2 and not A1 and A0?
Yeah, exactly. So there's only one possible input where this could equal, or where this should produce a 1. So the only time that this will produce a 1 is if, A2 is 1, and A1 is 0, and A0 is 1. So this is the solution for the only time that this input will equal 5. And so this will produce 1 for the one single case when this input equals 5. And then similarly for equals 3, it will be A2 and then A1, A0, except A2 will be inverted because we want, of course, the first bit to be 0, and then we want the others two to be 1. Like if we write out 3 in binary, right? So we want the first bit to be 0, then we want the next two to be 1. So this would be the sum of products expression for equals 3. This would be the sum of products expression for equals 5. Okay, excellent, good. So now that we have these two cells, I want you to turn to the person next to you, tell them how you implemented a circuit now that has a counter, and it counts up, but it freezes. It has this little glitch at 3, and on 3, instead it outputs 2, and it also stops at 5 and doesn't keep incrementing after 5. So go and spend 1 minute and tell the person next to you how you implemented this, and see if you agree, see if you disagree. Okay, begin. All right, cool. So first, let's just draw a counter, just a basic counter. So of course, that structure will look like you have a flip-flop, and then you have an adder going in, and then usually your input would be 1. So this is just a typical counter, right? It will start out probably as 0, and then that will pass into the D input. Next cycle, add 1, so it'll be 1. It'll add 1, 2, add 1, 3, add 1, 4, add 1, 5. So it'll keep adding. So this is how a normal counter works. But but now we need to use this equals 5 and equals 3 modules to slightly modify this design. Okay, so how do we make it stop at 5? Let's just take, one step at a time. So how do we make it stop now at 5? Yes?
You could connect the mux to the output with 5 is one of the inputs, one of the outputs is one of the inputs, and then the selector bit is the equal to 5.
Okay, so starting out, so you said connect the...
the output as one as an input, and then also just 5 as one.
As an input to a mux,
Yeah.
like this?
Yeah.
Okay, I will bring this over here. Okay, sure.
And then 5 as an input.
Got it. Okay, so you're saying input like this, 5.
And then the selector bit would just be equals to 5.
And selector bit is equals to 5. And this will probably also grab Q. I'll just say Q right here. Whatever, Q. Okay. And then what?
I have that. I think I put that to my output. I don't know if I put it back.
Yeah. So I think we're close. We could do it this way. I think what would probably end up happening is instead of Q, what would probably we pass in right here? Can we be more specific?
First iteration.
We would probably pass in the output of the adder. Yeah. Okay. So we could try that. So we could probably. I'll just kind of do this quickly. So yeah, we could probably instead of passing in this, pass in the adder, and then finally, then this now will go into this, and then the adder will always be connected to 1. Yeah, this would, in fact, halt it now on 5. Yeah, and we would see that, so the data could come out of Q, would go into this adder, and then we would decide, well, do we use the output of the adder, or do we just use like 5? Like, do we use the maximum value? Like, do we either add 1, or do we use the maximum value? Yeah, this is definitely one way. What is another way that people held value constant at 5? Let me just kind of reverse this really quick. Okay, what is the other way? Yeah.
I just had a question for that previous one.
Uh-huh.
Would there also be a possible way for it to work by feeding it into the adder after?
You're saying put a mux after the adder?
No, but like how you were saying, like to put the output of the adder into the mux.
Uh-huh.
How you switched it?
Uh-huh.
You could have done it the other way too.
Right. You're saying put the mux output into the adder?
Yeah.
Sure, yeah. Can you walk me through that?
Yeah. So you can start the mux,
Sure.
and then have the selector be the equals to 5.
Okay.
And then like one of the inputs to the mux would be 0.
So for the one case, so when it equals 5, then what should we pass into the adder?
0.
Yeah, if it equals 5, then we probably just don't want to add anything. But if it does not equal 5, then what do we want to add? So we're already adding Q, so we would probably add 1. Yeah. Right. Yes, exactly. Yeah. So, and this is how I already explained the homework question. The counter that counted up to 4. I personally like this structure a little bit more. Just I feel like it makes a little more sense to me. But yeah, either one totally works. Okay. So this is good. Now let's worry about how to make it kind of freeze at 2. So how do we do that? Yeah.
I would have another mux on the output.
Okay.
And for that one, I would have the selector bit
Yeah.
equals 2.
Equals 2?
Or equals 3.
Equals
Yeah.
3. Okay.
And then for the 1 selection,
Uh-huh.
I would set that output to 2.
So we're saying if it equals 3,
Yeah.
then output 2. And then for the 0 case, what do we output?
Just the Q from the flow block.
Yeah, there we go. Sure. Yeah, absolutely. So now if we were to store maybe 1 right here. No, if we store 2, yeah, that's probably better. So if we store 2, then what will happen is we will pass into here. Is 2 equal to 5? No? Okay. So therefore we take the 0 case here, and then we would add 1. So then on the next cycle, it would equal 3. Okay. Also, if we were currently were storing 2, then what would the output of this mux be? 2? Yeah, okay. So now let's check what happens on the next cycle. So on the next cycle, then now it transitions to 3. Okay. And so now 3 comes in here. Well, is this equal to 5? No, still not equal to 5, so then we add 1, so this now transitions to 4. But now we pass in 3 into this equals 3 module. Is 3 equal to 3? Yes, so we take the 1 case, so therefore we output 2. So it looks like it is in fact working. Okay, does this make sense? Maybe it's a little bit cruel to show you like the solutions when you haven't like received your grade yet, but hopefully this makes sense. And yeah, just drawing out schematics like this, drawing out circuits, thinking like, okay, where can I put muxes in order to change the output to whatever I desire? This is absolutely crucial. This is probably the main takeaway of this class. It's like, can you, given a problem, can you draw out the circuit that solves the problem? So yeah, definitely spend some time thinking about this. I will get your solutions to you shortly, hopefully within the next week. Yeah, question?
Oh, never mind.
Okay. Cool. Any other questions? Any other questions on anything else on the midterm? Yeah. Okay. Cool. Good. So, 9:48. I published homework 4 as well, so please start homework 4. We will talk about how to do a few of these questions in the remaining bits of lecture. Yes, so please go and read through this, start this as soon as possible. I will say that there is this question down here, which requires the lecture recording that I posted on Monday. So make sure you watch that lecture recording. It will significantly help you with this question. I may have made a mistake where I accidentally went over this exact question. I meant to go over a slightly different question, but I think I accidentally just went over this question. So yeah, so I apologize for that. So I'll probably go over another example like this just to give you more practice on this style. But it can be a little bit, it's like kind of amazing, I would say. That was like kind of my first thought when I first saw this, when I was first learning Verilog. It's like the idea that you can actually have if-else statements in Verilog, and then it will actually create a circuit. And this is on the backs of maybe 50 years of programming languages, theories, and also just like, I don't know, how we think about logic. It's just really, really cool. And the same algorithms that are used to generate hardware from a string of code like this is actually very similar to the algorithms used to optimize like C++ code and reduce the number of branches and if statements and things. There's a whole branch of research in algorithms and in programming languages, all based around decision trees. I don't know if you've heard about decision trees, but it's a huge aspect of computer science, and it's just really cool that as hardware engineers, we were able to take advantage of that research topic and be able to write hardware that is very human readable, to where anyone can kind of just look at this and understand what the behavior of the circuit is, even though that this potentially will create like a very large net list that would be confusing to look at like as just a bunch of pictures like drawn together, versus this is like much more readable. We can add like comments and things. So okay, good luck on this question. Please go back and watch the Monday lecture that I recorded. Okay, cool. So state machines. Okay. Can anyone give me a definition of state machines? It's kind of a vague sort of term in my opinion. Yes?
I define it as like a machine that can be multiple states characterized by like a Markov chain.
Sure, absolutely, yeah. So a state machine is a system that can have multiple states, characterized with a Markov chain. Sure. So what I kind of like to think about is, well, all digital circuits, since we only have binary values, there's only a certain number of states that our circuit can have. So I would say a state machine is like the realization that your circuit can only have so many states. And so a state machine is the idea that you combine your user input and you combine whatever state your system is in. And that is what defines both the output and defines whatever the next state is. So a state machine is just a system that has a finite number of states. You may also hear the term finite state machine. Okay, so here is a circuit that we've already looked at in class, but we could characterize it as a state machine now by drawing out this like bubble diagram. And so what is missing from this diagram? So I have these bubbles right here, but what are the things that I would need to add to this to explain what is happening in this state machine? Yeah. Yeah, exactly. We need to just have arrows that denote the transitions. Okay, so let's do that. So for the case, so first let's fill out this truth table, this like transition table, and let's also assume that maybe the output right here is just going to be the same value as Q. So y is equal to q, so therefore we don't need to actually store what the output is in this transition table. Okay, so if we have, so I'm going to go through each of these. Can you just shout out what the value of d will be for each one of these states? Okay, so for this first one, what is it? 0, yeah, because we have x ANDed with what was stored in the flip-flop. So first it is 0, then what is next? Yeah, 0. Then what's next? 0. And then finally, if we have a 1 ANDed with a 1 in the flip-flop, what do we have? What is it? 1. Yeah, perfect. Okay, so now if we have our states right here, so q equals 0. So what happens? So we can see that for q equals 0, which is this case and this case, we can see that no matter what, it actually looks like we will always be transitioning to what state? So if we were in the 0 state, what will the next state always be? Thank you. Yeah, 0. So this just shows that no matter what the input, so say x equals 0 or 1, then no matter what, we will transition back to the 0 state, okay? And now let's see how that's different for when q is equal to 1. So when q equals 1, then now it looks like, depending on what x is, we will transition to one or the other. What is the value of x, which transitions us into the 0 state? Yep, 0. So when x equals 0, we transition to the 0 state. When x equals 1, then what happens? Yeah, we stay 1. Okay. There we go. So if you were given this question where it's like, oh, here's a circuit, draw out the transition table, okay, so that's that, and draw out the bubble diagram, that's that. So if you ever receive that question, this is what is expected of you. All right. Questions? Sense? So, okay, I will move on to a slightly more complicated example. This is another example that we have already looked at in class, but okay, let's now draw this out as a transition table and bubble diagram. Go and take 1 minute first, copy down this question, try to get a head start, see if you can fill out the entire transition table, and then maybe start on the bubble diagram. Yeah, take 1 minute. Feel free to work with the person next to you. All right, it's quite a large transition table, right? So how many inputs, do we have to consider for our transition table? Yeah, there's 4 whole things we need to consider. We need to consider A, B, and then Q1, Q0. Yeah, so it's quite unwieldy. So actually, in this case, it's best not to draw a transition table, right? I've kind of led you on a little bit, and I'll show you kind of what mine started to look like. It takes a long time to even write out the table. That is why thinking about circuits as state machines is so valuable, is because we can draw a transition diagram that perfectly demonstrates the behavior of the circuit without needing such a long transition diagram. Because yeah, even this is only half the size. It would be whatever, something it's super long thing. Oh, I broke it. Okay. Yeah, it'd be like this super long thing. So it would take forever to fill out, and then we have to do it twice because there's two separate inputs. Fortunately, yeah, we don't really need to worry about that because with state machines, we can just skip right to a bubble diagram like this. And we will see that it actually ends up making things quite easy to look at. So let's do that instead. So how many possible states do we now have? So we have two flip-flops. So how many possible states can we have with two flip-flops? We can have 4 whole states. Yeah, either 0, 0, 0, 1, 1, 0, 1, 1. So we have 4 possible states. Okay, let's say we had 3 flip-flops. How many possible states would we have? 8. Yeah, 2 to the 3. Yeah. We would have whatever 0, 1, 2, 3, 4, 5, 6, 7. Those are all possible states. Yeah. So if we wanted to have a state machine with, let's say, 11 states, then how many flip-flops at minimum would we need for 11 states? Yeah, I think we would need at minimum 4 because there's no way that we could put 11 states into just 3 flip-flops because the maximum number of states, remember, so the whole idea with state machines is there's a finite number of states that our circuit can be in, and so we need enough memory on it to encode all of the different states that we have. Okay, so but let's just worry about this one, not an 11 state machine. So the 4 states will be 0, 1, 2, and 3. So let me write that out. So I'll call this one 0. Yeah, that's fine. Oh, let's see. Wow, that's annoying. Okay, that's fine. Okay, 0, 1, 2, 3. Okay, if we are in the 0 state, and if we look at this, so 0 state meaning both of these are 0, then what input will cause us to change our state? What is it?
B equals 1.
Yeah, b equals 1. What happens if b equals 1? What is it? Which one? Sure, so x0 now will become 1. So what will now this next state be? Will be 1, 2, or 3?
1.
Yeah, it'll be 1. So what we have, yeah, so we will have that that if we are currently storing 0, but if we receive b equals 1, then we see that x0 will transition to state 1. Okay, and that is all that can happen. We can say otherwise it will just stay back to itself. And honestly, we could probably just not draw this like loop back thing. I'll leave it just for a visual, but yeah, anytime that we have something where it loops back to itself, I would say in bubble diagrams, that's going to be the default case usually. You often have like very few times where you actually change states. So by default, you can just assume that it's always going to loop back to itself. So this isn't really needed, but I will say whatever, OW for otherwise. And I'll say not needed. Okay, cool. So now, if we are in state 1, so we are now storing a 0 and a 1 here. Well, what happens if, so what is now the new input that we care about that will cause us to change state? If you're now storing 0, 1. Sure, so what happens if A is 0?
0.
Can we be more specific? What state will be next if A is 0? So if A is 0, and it's ANDed with the value that's stored here, so this is storing a 1, so we have 1 and 0, so...
1. Back again.
Yeah, okay. argue with the person next to you. What is the answer? Okay. Okay. If A is 0, we actually have that it just stays where it's at. Because if it's currently storing 0, 1, and then we have 1 ANDed with 0, then now the output will still remain 0 over here, and then we can assume that the 1 is still here, unless, but now we need to look at whatever B is. Okay, so if B is 1, then yes, it looks like it will stay the same. If B is 0, then what will happen?
0.
Yeah, so in that case, it actually does look like it will receive 0. So I guess it depends on both A and B. So let's denote that though. So what was the case when we had it loop back to itself? So I'll say AB equals what value? So I think 0, 1. Okay. And then what happens if we have 0, 0 passed as our input? Then what is the next state? Yeah, I think we go back to 0. So if AB equals 0, 0, okay. And then we have 2 more like possible inputs to worry about. So what happens if AB is 1, 0 now? So if we are currently storing 0, 1 and we receive 1, 0, then what will the new state be? So it looks like we have a 1 that's fed into this AND gate, a 1 ANDed with 1, so now we're going to have a 1 over here, and we will have a 0 over here. So therefore, it looks like it transitions to what? To 2, yeah, okay. So in the case where we have 1, 0, so AB, I'm gonna skip the AB equals part, I'll just say 1, 0, okay? And then finally, if we have 1, 1, then what will the output be? Yeah, it'll just go all the way over. Sure. Yeah, and notice that kind of interestingly, it looks like whenever we are in this state, it looks like AB will just determine exactly like what state it goes to. So if AB is 0, it goes to 0. If AB is 1, it goes to 1. If AB is 2, it goes to 2. If AB is 3, it goes to 3. Yeah, not something that is entirely recognizable if we just had like a big, truth table. Now we can very clearly see like, oh, okay, so that's what happens when A, B equals that. So this is a very visual and yeah, just useful way of looking at all the possible states. Okay, so we are halfway done. We have 2 more states. Let's see how fast we can go. So if we are now storing 1, 0, in other words, if we are in state 2, so we're storing 1, 0, okay, what happens if we have 0, 0 here? As the input 0, 0. So one thing that you can know, so anytime that you have a 0 passed in for A, we know that we will always have a 0 over here. So therefore, yeah, so if we are storing, so if we're in state 2, we know that we will have the first bit cut off, so it'll either be one of these 2 states. And then, yeah, but if we have now a 0 passed in, well, it's ORed with this 1 that's stored. So therefore, we'll have a 1 over here. So what state will 0, 0 give us? Is that right? That is right, yes, right. So when we have 0, 0, it goes to 1, okay? And when we have 0, 1, so when B is now equal to 1, will that change anything? No, it looks like it will still go back to 1. So I'll draw another arrow that's like 1, 1. Now it's getting a little bit congested, but that's okay. Okay? And then now if we have 1, 0, so A is 1, then what happens? So we have 0 ANDed with 1, so that will produce probably a 0. Then we have 1 ORed with 0, that will produce a 1. So what will the next state be? What is it?
1.
Yeah, 1. Okay. So it looks like in that case, when we have 1, 0, it will also go back to 1. Okay. Then finally for 1, 1, then what will the output be? What was that? 1, 1. So if we're storing a 0 though in this, then now A will, wait, is that right? Yeah, I think that will still give 1. Because if 1 is passed in for A, we still have a 0 here, so this will now produce a 0 over here. And then for B, we have 1 and 1 being given into this OR gate, so then this will produce a 1. So it looks like no matter what, if we are ever in state 2, it looks like we will always transition back to state 1. Is that what we're seeing? Did I make a mistake? I think that's right. Okay, so in that case, I'm actually just going to erase all of these little arrows because it would be much cleaner and clearer if I just have an arrow that is just always pointing to that. So I'll say always. Okay, and finally we have one final state. So when we have 1 and 1 being stored here. So if we have now 0, 0 passed in as A and B, what is our next state? So we know that we're going to have a 0 here. And what will we have here? 1. So therefore, if we are given 0, 0, then what will our next state be? 1. All right. Okay. Yeah, so if we have 0, 0, that will give us 1. Okay, if we have 0, if we have 0, 1, then what will that give us? So we will still have a 0 passed in for A, so this will produce a 0 right here, and now we will have a 1 passed for here. So it looks like for either 0, 0 or 0, 1, we will transition back to A. So I'll put a little slash here, and I'll just say 0, 0 or 0, 1. Okay. What happens if it is 1, 0? What is the next state? Yeah, I think it's 3. So 1, 0. Okay. And then finally, for 1, 1, what do we have? So for fed in the input 1, 1, then our next state will once again stay at 3. So I'll put a little slash here.
When got to?
So if we are currently storing 1, 1, and we also take in 1, 1, then the next state will definitely stay at 1, 1. Okay. Well, notice something here. So how can we now? Okay. So get back on board if maybe you fell off. So this is the state transition diagram for this circuit. Okay, this is the transition diagram. Now, if we look at these transitions right here, so we are in state 3, and when we have the case for 0, 0 or 0, 1, notice that we transition to 1, and when we have this the input 1, 0 or 1, 1, then we transition back to 3. So notice these two arrows. How can we simplify these to now, or make them a little bit clearer? How can we make this diagram a little bit clearer instead of just adding this slash right here? So this one right here, what could we probably write instead of this? Yeah.
A equals 0.
Yeah, exactly, right? So when A equals 0, notice that we don't care what B is, because B can either be 0 or 1. So right here, I would probably just write when A equals 0, then we take the transition to state 1. So say A equals 0, and then right here, what can we replace this with? A equals 1, yeah, exactly. Because notice that we don't care what B is, it can be either 0 or 1, but we do care that A is equal to 1. Yeah, so there are a bunch of different ways we could have drawn this, but this is probably the most kind of clear diagram. And it's very important that as you go forward and anytime you're asked to draw a state transition diagram, either on the lab or in homeworks or on the final, you must always be sure to draw your diagrams as cleanly, neatly as possible. And that means that if you have multiple arrows pointing places, think, well, okay, are there ways that I can simplify this? It's not like if we don't care about one of the inputs, then maybe we can just throw it out of our schematic. Maybe we don't need to worry about, if we don't need to worry about what B is, then we shouldn't even include it in our diagram. It will just make things clearer if we can kind of just pull things out. But you now will notice, right, even though we had this massive 16 input truth table, it all simplified down into this quite neat transition diagram. So that is the benefit of thinking about circuits in terms of state machines, is that it's just a cleaner kind of model to help you design systems, large systems with a lot of possible inputs and outputs. But this right here will simplify all that for you. Okay. Yeah. Any questions on this? I will also say that state machines, they're fantastic. They're in everything. They are kind of a difficult topic to lecture because it's like you're just kind of like, all right, like now we pass in this input. What's this going to be? And it's like after like 10 minutes, I've taught state machines like 3 times now, and every time at least one person falls asleep. And but fortunately, I don't see anyone actually sleeping. So I would say this has been successful so far. But yeah, I will say that it's something where it's a little bit hard to pay attention in lecture, and then when you get to your homework, you're like, oh no, I should have not fell asleep or something. So, okay, cool. Yes, I want to do a participation quiz. What determines the next state and output of a state machine? Okay, what does determine the next state and output of a state machine? Yes? The inputs, what's the other thing? Yes? And the current state, yes. So those two things combined, that is what determines both the output and also what the next state is. That is the whole purpose of state machines, is you combine the current state and you combine whatever input is being fed in. Okay, thank you everyone. I will see you all on Friday.